Okay, so I'd like to talk a little bit about a spring scale. So we're going to look at a spring scale like this one here. This is more or less what you'd use in a physics lab or something like that. But, I really would like you to think about these grocery store spring scales that, are out of fashion now, I think. I think everything's digital. But this is what, you know, you used to see when you went to a grocery store and you were buying vegetables and you wanted to weigh them. You had a spring scale like this. This is a little bit more complicated, however. This guy has some stuff on the inside, so we'll just look at this spring scale here. We're going to say that this spring scale, this is actually much longer than that. Well, not that much. That's probably an inch there, so that's one. Well, let's do this full range is 1, 2, 3. That's actually about the right size, about 3 inches. And then we want to figure out how stiff the spring is. How stiff is our spring if we want that full range to be 6 pounds? Like this guy's 10 pounds there. We want 6 pounds probably because that makes life easier, right? But strangely enough, that's how I choose my numbers. So let's see what's going on here. So here is actually, this guy is the box here. This is the thing you're measuring. And we're going to analyze the thing we're measuring to figure out how much the spring extends. So the spring is going to be pulling the box up. So the tension in the spring is going up. And then there's going to be some weight coming down, right, from the box here. Or from your apples, I think those are. Your apples down there. So we want to figure out how far down that spring goes. Right, and so that means it's going to have zero net force. So this guy is not going to be moving here, right? So nothing's pushing or pulling it or anything at all. So we should give these axes some labels as well. So that gives us more or less what that free body diagram looks like. That's the physics here that's going into this thing staying still. Staying still and the forces on it. So that's the physics. We'd like to translate that into math so we can get some numbers, some idea about what we actually do, right? We want to actually figure out what spring we should buy to make this scale. So we start off with our free body diagram and turning this into an equation. So on the left-hand side, you have the forces. You have the tension in the spring going up. And we have the weight of the box, or the weight here, or the apples there, going down. And this is a situation where it's stable, so that's Newton's first law. That means this is equal to 0. Nice stable situation using Newton's first law. So that now lets us do stuff with the tension and the weight. I guess the first thing we want to do is we want to say, every time we see this, we want to do the same thing, basically, which is if the tension minus the weight is equal to 0, that means the tension is equal to the weight. You always want to do that. If something's equal to 0, that means on one side, then that means the other things are equal to something. We're not going to have really complicated questions, so we don't have to worry about what goes on left and what goes on the right. Most of the time, actually I'll have an unduly complicated question next. So my next example, which will be springs in series and parallel, will be unduly complicated. All right, so then we want to take the tension and turn it into something. So remember, for the spring force, the tension is equal to the spring stiffness. That's the thing we want, so that's good, times the extension of the spring, all right? And actually what we care about there is the maximum extension, which is going to be 3 inches. So that's going to be kx is equal to the weight, and the magnitude of the weight is going to be mass times the gravitational acceleration. But we're using pounds, so something special will happen. So how do we do this? Well, I guess the first thing to do is just write stuff down. The thing we want, k, goes there, times the maximum extension, which is 3 inches, which is going to be equal to the mass, which is 6 pounds of mass times the gravitational acceleration. We can simplify that a little bit because 6 pounds of mass on the surface of the Earth is equal to 6 pounds of force. Now that's the scary thing, is if you're on the moon, that's not true. 6 pounds of mass and 6 pounds of force are different numbers, would indicate different objects. So to get 6 pounds of force, you need something much heavier on the moon. But here on Earth, 6 pounds of mass is equal to 6 pounds of force, and that's the reason why we use the things interchangeably. All right, then we need to, it doesn't look like inches, then we need to divide through by the 3 inches on both sides. Right. So that's going to give us 6 divided by 3, which is 2 pounds of force per inch. That's kind of okay, but we usually want to do these in feet for imperial units. So that's 12 inches over 1 foot is the conversion. Uh-oh, what did I do? I pressed the little button. Okay. 1 foot. Now I want to see what that button does. I didn't really look at those things. Now I'm curious. I'm curious, and I have to finish this up. Oh no! So I'll just finish it up. That's 24 pounds of force per foot. All right. So that's basically all we need to do to solve that problem. So this is a stability problem, right? So it's stability, and it's stability because this guy's not moving, right? As long as our test mass isn't moving. Oh, actually, I was right. I just had a funny angle to that eye. Because this guy's not moving. Let's see. So that means we have Newton's second or Newton's first law, which means that we have no net force. All right. Since it is a force problem, we have to have the free body diagram. We have to look at what things are actually influencing this test mass that we're using to calibrate this spring so we know what we're doing. And that has two things going on. It has the spring pulling up on it and the weight coming down, and that's what we have here. Tension going up, weight going down. And so tension minus weight is equal to 0, and then we just do math from there. Remember T minus W equals 0 means T equals W. And then we do the substitutions of our definitions. And then we do our substitutions of our data. This is our data coming down here. And then we do mathy stuff. So these are fairly simple math problems. So I hope you don't have too much of trouble with that. We've been doing the conversion the whole way through just because it's fun. And then we know how to divide and stuff like that. So I think that will be sufficient for you today. Everybody's stuck at home now, so nobody's actually combing their hair, I'm sure. All right, so you have a very nice day. I hope this has been helpful, and I will talk to you again in a few minutes, my time. Actually, probably I'll go out and do some yard work because somebody else is doing yard work and I can hear it, which means you probably can, which means this is distracting to you. Even more distracting than me just talking about the lawnmower that I can hear through my headphones, right? My noise canceling headphones. So I don't want to know what it sounds like to you. Bye now.